Okay, we've been talking about the role that we've been talking about how to calculate hydraulic conductivity and how important it is in determining the rate at which water moves to the ground, right, through Darcy's law. But it turns out that when we think about Darcy's law, what we're really referring to is what's referred to as matrix flow. So matrix flow is what is governed broadly by Darcy's law, and that represents the movement of water in a broadly laminar fashion. We're not really going to talk about laminar and turbulent flow, but moving very evenly and smoothly and generally very, very slowly through the pores in some sort of aquifer. Well, it turns out that that certainly is very, very important, but in areas where there are fractures, then water can move along those fractures through a process obviously we call fracture flow. And fracture flow is really upsetting the apple cart. The more we learned about it back in the 100 years ago, 50 years ago, the more it really began to shape the way we evaluate groundwater flow. So, for example, you can imagine a scenario where you have a field, and here's north, and let's say it's a flat field, but the hydraulic gradient is, the equipotential lines, the lines that sort of contour the water table, contour hydraulic head, might look something like this, like 980, 970, 960, 950. So each one of those is the elevation of the water table, right? So we would expect then that the water is going to be flowing just like a ball rolls down the hill. The ball is going to be moving, perpendicular to each one of those lines. The water is going to be flowing in that direction, so that if there was a spill right here, if there was a spill of some sort of contaminant right there, we should be able to more or less predict where it's going to go. And if we had a sense for what the hydraulic conductivity of the rock is, if we knew the K of the aquifer, then it's a pretty trivial exercise to use Darcy's law, right, to say Q equals negative K dH dx. We can calculate the hydraulic gradient dH dx by using this information, the height of the water table and and its slope essentially. And if we know K for this rock, then we can calculate it, and we get velocities maybe, who knows, like just make this up, but maybe it's 10 to the minus 3 centimeters per second. Okay, so that's like 0.1 millimeters per second. So if you knew when this thing was spilled, you ought to be able to project how far the contaminant has gone in a certain amount of time using this velocity. And so people would try to apply this, and what they'd find is that instead of having gone this far, the plume had migrated, the contaminant had migrated, all the way down to here. And that was very confusing because Darcy's law is so straightforward. Well, it turns out that the explanation for this has these kinds of scenarios, is sometimes associated with the presence of fractures. So if there's a fracture, then the water moves according to something called the cubic law. And what this basically says is that flow through a fracture is proportional to the cube of the fracture aperture. Aperture being the width of the opening, right? Or width, how wide the crack is. So what does that mean? That means if you think of it sort of like this, right? If this is the width of the opening of the fracture, and this is the flow through the fracture. Right, here's 0. If the width is, I should do this in a different color so it stands out. It's not going to work. If the width is 1, 1 to the third power is 1. So that would be the, let me draw this again. That's getting too cluttered. So what do we have here? We have flow through the fracture, and we have the fracture opening. So if you have something that is, say, 1 millimeter or whatever wide, a fracture that's 1 millimeter wide, well then, 1 to the third power is 1, so that's that. But if you have a fracture that's twice as big, that's 2 millimeters, right? Now the flow through the fracture is the cube of 2, which is 2 to the third. So 2 times 2 times 2 is 8. So here we go. Here's 1, 2, 3, 4, 5, 6, 7, 8. So it looks like this. So you can, without even doing any more, you can see that the flow increases radically, very, very, very quickly as the fractures get a little bit bigger. And so any small fracture can conduct an enormous amount of water. And to illustrate that point, I'll show you a couple of figures. Hopefully this shows up. It's a little glossy. I think it's looking okay. We don't have to worry about these down here. Just focus on this thing. So what this says is, this on the x-axis is the thickness of a continuous medium equivalent to 1 fracture. So this is the thickness of an unfractured aquifer, unfractured rock. And you can see it's a log scale, right? So it goes from 1 to 10 to 100 to 1,000. This is in meters. So 1,000 meters is a kilometer thick. 1 meter is 3 feet thick, right? So this is 3 feet. This is 30 feet, which is a 3-story building. This is a 30-story building, and this is what, about half a mile thick. And then this is the aperture, the width of the fracture in meters. So 10 to the minus 3 meters is 1 millimeter. So this is a line going across here that says this, everywhere you see this line, this is 1 millimeter wide, a fracture. This line going across here is 1 centimeter wide, and this is 1/10 of a millimeter. So 1/10 of a millimeter, and a centimeter. All right, so how do we read this thing? Well, we can look at it like this. So this says if each one of these lines, these angled lines, has a number on it, 10 to the minus 3 meters per second, 10 to the minus 4, and so forth. This is the hydraulic conductivity of these rocks down here. So if you were to say, let's start right here. So right here we have a 10-meter thick rock, unfractured, that has a, go up until it intersects this angled line right here. That's a 10-meter thick rock with a hydraulic conductivity of 10 to the minus 4 meters per second, which would be 10 to the minus 2 centimeters per second. So 10 to the minus 2 centimeters per second, which is pretty high, right? You got 10 meters thick of rock, which has a hydraulic conductivity of 10 to the minus 4 meters per second, which is the same as 10 to the minus 2 centimeters per second. You could pump, if you have, for whatever given hydraulic head or hydraulic gradient you have, you could pump the same amount of water through a 10-meter thick chunk of rock with a hydraulic conductivity of 10 to the minus 4 meters per second as you could a single fracture, which is, now we're following this horizontal line over, a single fracture that is 1 millimeter thick. A more extreme example, maybe. Let's say that it's 1 centimeter wide, the fracture. When I say thick, I mean wide, right? So one millimeter is, you guys know what a millimeter is. You know what a centimeter is. It's about just under half an inch. If you had one fracture that was a centimeter wide, you could pump, for a given hydraulic gradient, you could pump the same amount of water through that fracture as you could, we'll go over to here, a kilometer thick chunk of rock with a hydraulic conductivity of 10 to the minus third meters per second. So that's 10 to the minus 1 centimeters per second, a kilometer high. For a given hydraulic gradient, the same amount of water would come flowing through that rock as one fracture that was a centimeter high. Okay? So fractures are enormously, enormously important. And of course, they're hard to know where they are. If you're dealing with rocks that are buried underground, how do you know if there's a fracture down there? It's very, very difficult to identify. It's very difficult to see them in well cuttings either. When you bring up a bore, when you bore into the rock and you bring it up and you look at it, those rocks break all the time. So it's hard to know if what you're looking at is a real fracture or not. So we can calculate the flow of water through a fracture as this. Q, which is, remember, volumetric flow. This is cubic centimeters per second or cubic feet per minute or whatever. Can be calculated as the density of water. That's what that stands for. Density of water, which is 1,000 kilograms per cubic meter, times G, which is gravity, which is 9.8 meters per second squared, times B cubed, where B is the thickness of the fracture, the width, the thickness, the opening, thickness of the fracture. W, where I'm running out of room here, where W is the width of the fracture measured perpendicular to flow. So what that means is if water was flowing in a fracture across the page here from the left to the right, we would measure this W perpendicular to the page. So from the paper up to some height, right? How high it is, it goes. Over 12 times this mu. Mu is the viscosity of water, which is just how gummy it is. And that has a value of 1.15 times 10 to the minus 3 Pascal seconds at normal temperatures, about 15 degrees, times dH dx, which is the hydraulic gradient. So this, you don't have to memorize or anything, but you should see this basic relationship, right? That the amount of water, that's flowing through a fracture, Q, right, the volumetric flow, is equal to the cube root of the width of the fracture, which is what we just talked about, times how wide it is, perpendicular to flow, which makes sense, right? The wider it is, the more water you can pump through. It's driven by the hydraulic gradient. If there's no hydraulic gradient, you don't get any flow, so of course you need that. And then these other issues related to the density of water, the viscosity of water, gravity, and so forth. Okay, so that's that. So for your homework, you'll be looking at the impact of fractures on groundwater flow.